Good morning, dear students. Last class, I told definition of binary operation, and even I have given some examples on number system with respect to addition, subtraction, and multiplication also. Set for example, set of all real numbers, set of all complex numbers, and set of all rational numbers. These are all binary operations with respect to addition and multiplication also. But in case of division, they are not forming binary operations. Like that, I have given some different types of examples also. Even I have given on set of natural numbers and on set of integers also. Set of natural numbers and set of integers, they are forming binary operation with respect to addition and multiplication also. But a set of integers, they are forming a binary operation with respect to subtraction also. Like that, I have given different types of examples on binary operations. Today we'll discuss about laws of binary operation. Laws of binary operations means which types of laws will come in case of binary operations. Now we have to discuss about them today. First, laws of binary operations means here. First one is laws of binary operations. Laws of binary operation. Laws of binary operation first. Laws of binary operation means we will see here different types of laws. That is a closure law, associative law, identity law, inverse law, and last one is a commutative law. Like that we will see here different types of laws here. See, first one is closure law. Closure law here. Closure law here. Closure means here, let's A comma B belongs to capital S. Then A star B belongs to capital S here. Here SB non-empty sets. You must mention here capital SB is always non-empty set. For all this what I given, what I am going to giving to all these laws. In all these laws we mentioned S, but S is the non-empty set here. Where S is the non-empty sets. Where capital S is the non-empty set here. Non-empty sets. Non-empty sets. Take for example this is n is a set of all natural numbers. For example for that I have given here for closure property. Example, n is equal to a set of all natural numbers 1, 2, 3, 4 up to and so on like this. Take with respect to addition. Now with respect to addition, a is equal to 1 belongs to capital N here. B is equal to 2 belongs to capital N here. Take with respect to addition, A star B is equal to A plus B, you define like this. Then 1 star 2 is equal to 1 plus 2 is equal to 3 belongs to capital N. Like that you can take, I have taken operation plus, otherwise you can take an operation multiplication. According to question, operation will come here. For example, I have taken the operation is addition here. A is equal to 1 belongs to capital N. B is equal to belongs to capital N. Then A star B is equal to A plus B. That is 1 plus 2. 1 star 2 is equal to 1 plus 2 is equal to 3 belongs to capital N. Like that we are going to checking with the help of numbers in case of closure property. That's what here closure property definition is. Like A comma belongs to S, then A star belongs to capital S, where S is the non-empty sets. Then this type of law is called closure law. Next we'll discuss about next law is associative law. associate languages. Associate language. Like SB non-empty sets. SBA non-empty sets. SBA non-empty sets such that if A comma B comma C belongs to cap S, then A star of B star C is equal to A star B of star C. Then definitely this formula must ensure satisfied by all these three elements. All these three elements. A star of B star C is equal to A star B of star C here. Say, for example, we'll take one set of natural numbers. On that only, we'll take one addition. Operation is one addition. With respect to addition, whether they are following, or they formed associative law or not, now have to check about that property here. Example for this is take a set of all natural numbers. The n is equal to the all natural numbers 1, 2, 3, 4 up to and so on like this. Now take with respect to addition, A star of B star C is equal to A star B of star C here. Take A is equal to 1 belongs to capital N, B is equal to 2 belongs to capital N, C is equal to 3 belongs to capital N here. You check with respect to addition. With respect to addition, they are forming or they are formed or they are following that associative law or not, have to check with the help of all these three numbers here. So with respect to addition, if you can take here A plus of, that is A plus of B plus C is equal to A plus B of plus C here. A is equal to 1 here, 1 plus of 2 plus 3 here. Yes. Like that, we are going to giving example for associative law is associative law formula is here A star of B star C is equal to A star B of star C here. Take for example, take a set of all n natural numbers. N is equal to here 1, 2, 3, 4 up to and so on like this. A is equal to 1, we can take belongs to capital N here. B is equal to 2 belongs to capital N here. C is equal to 3 belongs to capital N here. Now take with respect to addition, whether they are following binary operation, whether they are following associative law or not here. See here A is equal to 1 belongs to capital N, B is equal to belongs to capital N, C is equal to 3 belongs to capital N here. Take addition. A star of B star C is equal to A star B of star C here. Take addition. A plus of B plus C is equal to A plus B of plus C here. Instead of A comma B and C, we substitute all these three numbers here. A is equal to 1 here. 1 plus of 2 plus 3 is equal to 1 plus 2 of plus 3 here. 1 plus 5 is equal to 3 plus 3. 6 is equal to 6 belongs to capital N. That you can check by multiplication also. That's why with respect to addition and multiplication, they are forming associative law. Just I am giving an example how we are going to checking associative law here. Next one is existence of identity law. Existence of identity. Existence of identity. Existence of identity. So identity elements. So identity elements or identity larges. Existence of identity element here. Let S be non-empty sets. Let capital S be non-empty sets. S be a non-empty set such that for all A belongs to capital S, for all A belongs to capital S, then there exists E belongs to S, then definitely this formula will be satisfied. A star E is equal to E star A is equal to E. This is the identity of formula. Inside you can take any elements. For all A belongs to capital S, then there exists E belongs to S. Definitely A star is equal to E star is equal to E here. For example, set of all integers you can take. Example, set of all integers z is equal to here. Take some set of all integers. 0 from verse 1, 2, 3 up and so on. Here minus 1, minus 2, minus 3 up and so on like this. Minus 1, minus 1, minus 2, minus 3. Here 1, 2, 3 up and so on like this. Take any one elements. For example, 2. A is equal to 2. You can take here. With respect to addition, how to check? 2 plus 0 is equal to 0 plus 2 is equal to 2 here. A star E is equal to E star A is equal to A here. A is. A star E is equal to E star A is equal to A here. Then what about E here? E is the identity elements. 2 plus 0 or 0 plus 2. Common 0 is the common for 2. It is the common element. That's here also 0 is the common element. 2 plus 0 is equal to 0 plus 2 is equal to 2. That's why 0 is an identity element with respect to addition. With respect to addition is always 0 is an identity element. Well, you can take with respect to multiplication also. This is example with respect to addition. This is with respect to addition. With respect to addition, this is. It is with respect to multiplication now. 2 into 1 is equal to 1 into 2 is equal to 2 here. That's why 1 is an identity element with respect to multiplication. Here 0 is an identity element with respect to addition. Here 1 is an identity element with respect to multiplication. This is example with respect to multiplication. This is. Like that we are checking the identity element with respect to addition and with respect to multiplication. Anyhow, if they can give definition means, but we must have to apply this formula to find an identity elements. What is an identity element formula? A star E is equal to E star A is equal to A. And what about E? E is the identity element. If we can take 3 also here, or if we can take 4 also. That's what I have written here. For all A belongs to capital S, then there exists E belongs to capital S. Definitely present in that set E, where we are calling E is an identity elements. We can take 3 also. 3 plus 0 is equal to 0 plus 3 is equal to 3. 0 is an identity elements. Otherwise, you can take with respect to multiplication also. 3 into 1 is equal to 1 into 3 is equal to 3. That is where 1 is an ident element. But we are taking this with respect to multiplication. Here with respect to addition. That's why in case of integers, we can tell with respect to addition is an ident element 0. With respect to multiplication is ident element is 1. Like that we are checking the ident element in the given sets. Next one is existence of inverse elements. Fourth problem. Existence of inverse elements. Existence of inverse elements. Inverse element here. Let S be a non-empty set. Let S be a non-empty set. Let S be a non-empty set such that if for all A belongs to capital S, then there exists A inverse or A inverse belongs to capital S, or we can write this as B belongs to capital S. Instead of inverse element, you consider it with the letter A inverse, that is A power minus 1, we are calling it as A inverse, or in some textbooks, instead of A inverse, they are going to take small letter B also. B belongs to capital S. Then A star A inverse is equal to A inverse star A is equal to ident element E here. Or in some textbooks, formula will be like this: A star B is equal to B star A is equal to E, where B is the inverse of an element A here. Where B is the we're calling where B is the inverse of an element A. That's what we can take instead of A inverse. We can represent with letter also A power minus 1. Or instead of that, we can take letter B also. A inverse is equal to B here. Here, A inverse is equal to B here. A inverse is equal to B here. A inverse is equal to B here. That A and B are they are inverse to each other. But how to check A inverse element with respect to addition and with respect to multiplication? Just I am giving examples only here. But pattern is different to find inverse and identity. According to problem, according to definition of given problem, then we can find identity element with the help of their definitions here. But just I am giving examples how to find out inverse element and identity element with the help of number system. And before that also, in case of associative law also, I have given examples with the help of number system. Even how to find out identity element also I told in case of set of all integers. And even I am going to giving say some taking real numbers or taking real numbers. If you can take set of all real numbers in that number system, how we are going to finding identity element and inverse element here. First one is inverse element here. Inverse element means already I told also one is an identity element with respect to multiplication and 0 is an element with respect to addition also. See here A is equal to 2 here. 2 plus is equal to 0. What by writing which letter you are getting 0 here? Minus 2. Or you can take here minus 2 plus 2 is equal to 0. That's what you can write. 2 plus or minus 2 or minus 2 plus 2 is equal to 0. But where minus 2 is the additive inverse of plus 2 and plus 2 is the additive inverse of minus 2. Like that, they are the additive inverse to each others. Minus 2 plus 2 or 2 plus of minus 2 is equal to the result of these in both cases result is 0 only. That's why when you are going to ident element 0 with respect to addition, then 2 and minus 2 they are inverse elements to each other. Like that, we are going to finding an identity element in case of addition. Next one is with respect to multiplication. This is the with respect to addition. With respect to addition. With respect to addition Next, with respect to multiplication, how we are finding an inverse element with the help of an identity element here. Say, I defined like all these examples now on set of all real numbers only. Inverse elements. See here. 2 into 1 by 2 is equal to 1 by 2 into 2 is equal to 1 here. Because see, by checking this here, 2 into 1 by 2, 2 into 1 by 2, 2 gets cancelled is equal to here 1. Or 1 by 2 into 2, 2 gets cancelled here 1. That's why 1 by 2 is the multiplicative inverse of plus 2, plus 2 is the multiplicative inverse of 1 by 2. They are multiplicative inverse elements to each others, 2 and 1 by 2. Or you can take 3 and 1 by 3 also you can take. 3 into 1 by 3 is equal to 1 by 3 into 3. On gets cancellations, you are getting element is 1. That's why in both cases result is 1. Result is 1 means already I told now 1 is the multiplicative, 1 is an ident element with respect to multiplication. Or 5 into 1 by 5 is equal to 1 by 5 into 5. Or 6 into 1 by 6 is equal to 1 by 6 into 6. Like that, you can take any elements. In case of set of all real numbers, you are getting an ident element 1 only with respect to multiplication. That's what here 2 and 1 by 2, 3 and 1 by 3, or 6 and 1 by 6, 5 and 1 by 5. They are all opposite each other inverse elements. They have inverse elements to each other respectively. Like that, we are finding the inverse elements here. By showing this example, easily we can analyze and easily we can tell 2 is an inverse element of 1 by 2 and 1 by 2 is inverse element of 2. Or 3 is inverse element of 1 by 3 and 1 by 3 is inverse element of 3. 5 is inverse element of 1 by 5 and 1 by 5 is the inverse element of 5. Like that, we are giving definitions and at the same time we are giving examples for inverse element in case of set of all real numbers. Next properties or next law is commutative. Commutative law. Commutative analysis. Let S be a non-empty set. Let capital S be a non-empty set. Such that if A comma B belongs to capital S, then A star B is equal to B star A. So left right perfectly satisfied by this law by any two elements of S, then we are calling that law as a commutative law. A star B is equal to B star A here. A star B is equal to B star A means take any numbers. For example, take natural numbers here. Example here. Example, take a set of all natural numbers. N is equal to 1, 2, 3, 4, up to and so on like this here. Take with respect to addition, with respect to multiplication. In these two cases, this set of all real numbers always commutative. How means I should know. Set of all natural numbers, set of all integers, set of all rational numbers, set of all real numbers, set of all complex numbers. These are all satisfied by commutative with respect to addition and multiplication, not in case of minus and not in case of division. Just I am giving examples on addition and multiplication because in these two operations only they are forming all commutative laws, associative laws, and even I showed how to find out identity element and how to find the inverse element also. Now let us we are discussing about commutative law. Whether I have given one set that is a set of all natural numbers, whether they are forming a commutative law or not here. Say here, check. A is equal to one element, one belongs to capital N here. B is equal to 2 belongs to N here. First, with respect to addition. With respect to addition, first formula is A star B is equal to B star A here. That is A plus B is equal to B plus A here. Take some elements here. Have taken 1 and 2 now here. 1 plus 2 is equal to 2 plus 1 here. 3 is equal to 3. Therefore, this is star is commutative with respect to addition also here. Next, we can take with respect to multiplication also. See here, with respect to this is with respect to addition. With respect to addition, this is. With respect to addition, this is. Next, we can check with respect to multiplication also. A is equal to 1 belongs to capital N. B is equal to 2 belongs to capital N. A star B is equal to B star A. That is A into B is equal to B into A. How to check about this law, this commutative law here. That is 1 into 2 is equal to 2 into 1 is equal to 2 is equal to 2. Therefore, it is a commutative with respect to multiplication also. LHS is equal to RHS. Here also in the case of addition, we go on to 1 plus 2 is equal to 2 plus 1. 3 is equal to 3. 1 into 2 is equal to 2 into 1. 2 is equal to 2. That is with respect to multiplication. This is with respect to multiplication here. With respect to multiplication. With respect to multiplication here. This is with respect to addition. This is with respect to multiplication. Like that, we are giving definition for commutative. At the same time, we are checking commutative with respect to addition and with respect to multiplication. Like that, I have finished 5 laws. One is closure law. Another one is associative law, existence of an identity element, existence of an inverse element, and commutative. Totally 5 laws I have given. But you know syllabus problems on associative, how to find variant element, and even how to find inverse element also there, and how to check the commutative also.
commutative and associative, identity and inverse. But there is no closure. In your exercise 1.4, all the problems they are belonging to associative, commutative, how to find out an identity element and how to find out an inverse element. Now let us start the problems from exercise 1.4 here.
First, problems from exercise 1.4. They will give one definition. At the same time, they are forming binary operations or not. About that, they are giving here. That is, just they are defining one definition with respect to any two letters on set of all integers or natural numbers or set of all real numbers or set of all rational numbers or set of all complex numbers as any one number set they will give here. See, first question, exercise 1.4, first question, verify, 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 star is binary operation or not, binary operation or not, or not, from the following definitions, from the following definitions. First one is on Z plus, on Z plus, define, define A star